presentation of the workshop. Regarding the program, we will have a very exciting series of presentations that will cover the most recent topics about imprecise probabilities and decision making. We will first get back to the roots of probabilistic beliefs with a presentation by Peter Wakker of the foundation of subjective expected utility. Then Glenn Harrison will show us how proper scoring rules can be used to elicit subjective beliefs under expected utility, but also under more general models like rank-dependent utility. Then Eddie Kearney will show how to elicit second-order probabilities. We will then have two empirical works that will be presented. One by David Tannenbaum that will show that the kind of uncertainty, namely aleatory or epistemic uncertainty, can impact the extremity of judged probabilities. Then Chen Li will present a paper that models deviations from Bayesianism in terms of imprecision in perceived signals. And then for the second part of the workshop, we will broaden the discussion to imprecise preferences or incomplete preferences. And Fabio Maccheroni will show us what happens to consumer preferences when noise is added to preferences due to time pressure, for instance. Then Chris Tarmer will report the results of an experiment where subjects were explicitly allowed to report incomplete preferences. And John Hay will give the last presentation that will elicit or test a model of satisficing that is welcome in cases where subjects do not have, decision makers do not have probabilities or have incomplete preferences. Thank you very much. Regarding the organization, we will have the lunch. We will follow Natalie to the restaurant. You have a Wi-Fi access with the login and password here. Those information are written on the program. Please do not hesitate to ask us any questions you have. And last thing, regarding the organization of presentations, we have 30-minute slots for each speaker. We can go for 20 minutes of presentation and 10 minutes of questions and discussion.
If no 45, 30?
45, sorry. So it's 30 for presentation and 15.
Okay. Yes. Okay. Thank you.
Well, we have 45 minutes. If we can devote 5 minutes at the end.
Yeah, that's good.
Questions, that would be
compulsory for every speaker. Yes, and the chairman will impose it. Very good. Because otherwise, you get boring conference if there are no questions. If speakers take all the time, shouldn't do so. Anyway, so this is a paper. When the first year that I did research, I did mostly theoretical work. The later years after the second half, maybe I did mostly empirical experimental work. But in the theoretical, in both of these, but also starting in theoretical, I was always using something called lemma of Hölder. That's a mathematics. I don't have the time to explain it, but I learned from a book, Foundations of Measurement by mathematical psychologist Kranzloo, Sapostversky, 71. I learned how to use that technique. And then I thought, I think this is the best, the most efficient technique for getting preference axioms, for getting cardinal utility functions, for instance. In economics, starting with von Neumann and Morgenstern, a mixture technique became popular. And all my life I thought, this mixture technique is not most efficient. They bring in a multiplication lambda that is redundant. The lemma of Hölder has only an addition operation, and that's enough to get any function you want. So I was always writing theorems and doing experiments based on that, and I enjoyed it. Anyway, recently Mohammed and I got together because I'm not the only one with that hobby. For instance, also Mohammed Abdalwi has, throughout his many theoretical papers that he wrote, also empirical, he also likes that technique, also used it a lot. So some time back, Mohammed and I got together and we said, let's try to convince people one more time that this is a good technique, and let us take the most famous, most impressive, most loved theorem in our field, and let us work on that. And that will be a theorem, well, I wonder if people should guess what is the most, maybe Adi, what would you say is the most famous theorem in our field? Yeah, Savage 54. I think most people, everybody has this. Savage 54 is the most famous, and it's a beautiful, impressive work. I think the gods were holding his hands when he wrote. Everything in his first 6, 7 chapters of his book is magic. The theorems, the interpretations, the words, like he introduced on the side a random incentive system for experimental economics. He was one of the first to write. Everything was very deep. He had intuitive axioms, technical axioms. It was also the technical axioms. They were very appealing, and they're mathematically very strong. It was unbelievable how beautiful and good and deep and important, etc., etc. it was what he did. Even more impressive is that in that year 54, preference axiomatization, you need that to justify a model. It's not just a mathematical game. You need it to prove observability. It's very important. But it almost did not exist in those days yet. There were maybe Phenomena Morgenstern had done it, and maybe 2 other people in some contexts. It was almost non-existing. So Savage himself had to invent how to do preference axioms. And then he came up with so beautiful that I think nobody ever has been able to get such mathematical power and beauty together. So it's very impressive. But now we still feel confident to return to it because we have, unlike Savage, we have more than half a century of extra literature and techniques. So maybe we can improve a bit. Especially we have this foundation of measurement book. And I think, so Mohammed and I said, we can, Savage maybe, he had phenomena. I think a roundabout part in his proof was his derivation that he went by Phenomena Morgenstern. He used this mixture technique. And I think this Hölder technique is more powerful. So Mohammed and I said, let us try to convince people, and I hope also today convince everybody that this Hölder technique is better. Let us take the most popular theorem existing in the literature and show what we can improve there. So that's what's happening today. And as many of you know, Savage, he gave a basis of precise probability. Most of today it will be about imprecise probability, but a good start, what we want to deviate from. Let us start with looking the precise probability, first get a foundation of that. So that's why the organizers like to start this meeting with a discussion of that topic, and that I will be doing. That's what Savage did. So as impressive it was also respected, but respected also means a bit looking up and being a bit afraid of it, because his proof was not written in the most easy way possible. So most people after 2 or 3, and also he leaves many things to the readers to prove, so it's not an easygoing thing. So most people admire, respect, but stay away. It's too difficult. So almost nobody has used his techniques, his framework. And now, of course, ambiguity is now a very popular topic. Many people are working on ambiguity, so let me already go here. And the Anscombe-Allman model is very popular because that's more tractable. Then you get linearity and you can use mathematical techniques. So that's why many people are doing it, and there are many pros to this model, but also cons. It will surely be interesting if we can get models, ambiguity and whatever, using the Savage structure, because there are many nice things in the Savage structure. So then we also hope that our paper, by making the Savage techniques accessible to wide audience, when I say dummies, I mean non-experts, because everything in our proof is completely elementary. You need to know nothing about mathematics, everything with figures. You can just easily understand and follow. And then, if you understand how it really works, what he does, people can use it also for ambiguity and other things. So that's also imprecise probabilities. We hope and we plan that there will be many works on imprecise probabilities using that structure. I mean, Savage structure, and as an alternative Anscombe-Allman. So that's a side reason why we wanted to work on this. Okay, so with that understood, let's go to basic definitions. State space, you know how it works. Subsets are events. We take an algebra of events. It need not be a sigma algebra. There's one point where we generalize. Only algebra of events. Consequences can be money, the consequence space can be anything general, finite, whatever. Completely general here. That's quite nice. Notation of an act. It's implicit in this notation that these E1, En are events from the algebra, partitioning the universal event. You get outcome x1 if E1 happens. You get xn dollar maybe, or euro, if En happens. That's how this notation works, usual thing. Preference relation over the acts. That's all the usual thing. Now, definition of subjective expected utility means there exists subjective probability and subjective utility such that this formula is maximized. So this is probability weighted average utility, expected utility. Typical things, these are not objective, but they are subjectively derived from preferences. A well-known model. One notation I'm going to use, so I explained to you. If I write here, we have some act, so a thing like that, act F, event E, outcome, consequence. I'll use the Savage terminology today, consequence. Consequent alpha, this means it is just like act F, but one thing changes. On the event E, we don't get what F would say, but we get alpha. So this is F with on E, things are replaced by alpha. That's the notation that I use a lot. So let me give an example. If here we have an act giving outcomes on events, I write this. That means on event E2, I replace whatever happens there by alpha. So then on event E2, you get alpha and not x2. So here is what this notation does. On event E2, we have alpha, and outside is business as usual. So that's the notation. So outline of my talk, let me give it only now. Introduction, we already had it. Then comes Savage's conditions, what Savage did, his theorem. Then how we change the theorem. And if you like it more, we like it more, in fact, a bit more. We change a little bit in this theorem. We make it a little bit more general. We think a little bit more appealing. But it's a bit of a matter of taste. We like it more, but you can see for yourself. Proof, conclusion, and that will be it. I'm going to start with Savage preference conditions. I'm going to start with the intuitive conditions, the conditions about preference and rationality. We don't change them. We're in the technical, the mathematical part. That's where we do our work. So I just list the conditions. Weak ordering, transitivity, completeness. The most important one, sure thing principle, but I think most people know what it means. Here is a notation for the sure thing principle. Sure thing principle means that if an event E where two acts have the same outcome, then the preference is independent of that outcome. So if we replace it by another common outcome, if we replace the common outcome alpha by the common outcome beta, that doesn't change preference. That's the most important condition. There's a beautiful paper by Moscati in Journal of Experimental Perspectives on the history. This condition was really the most important condition. It arose in letter correspondence between Savage and Samuelson. Samuelson, the great guy, the great spirit. And he, together with Savage, and then some misunderstanding, and then they got it. Savage got it, but really, and the history, the documenting those letters, a beautiful paper. Anyway, monotonicity of outcomes, third condition. That means if somewhere we see that gamma is better than beta, then we should see it everywhere. Then if we have already seen gamma is better than beta, wherever we can replace beta by gamma, it's an improvement. Monotonicity of outcomes, monotonicity of events. If anywhere, so gamma, I always like the notation gamma good, beta bad. In many papers of mine, it's like this, gamma better than beta. If you have two outcomes, beta, gamma is the better one, you can choose. Would you rather have the good outcome on an event B, and then beta everywhere else? This is constant beta, only on B you get gamma. Or would you rather have it under event A? And imagine you say, well, I'd rather have it under event B. Then here we observe, it looks like B is more heavy, more weighty than A. Well, if once we observe it, we should observe it everywhere. So that means in all situations, if we have other outcomes, gamma prime better than beta prime, we should see the same thing. We always consistently will find which event is the best. So if we have that, we can define a more revealed, more likely than relation. Whenever we see in a betting situation, you rather bet on one event than the other, we say then that one event is revealed more likely according to your subjective taste than the other. And that is a consistent thing. So we use the same symbol as preference relation. There are many good reasons to use the same symbol. This is also denoting the more likely than revealed preference relation over events. We can do it in a sensible manner thanks to that condition. We'll use it a lot. So well, I don't know, definition. Non-triviality, not everything is indifferent. So those are the 5 intuitive axioms of Savage. But then we need a bit more. We always need some technical condition, richness conditions. And Savage had a condition P6. Even now, I don't have the time to define it because, well, so I cannot define it. And one reason is because we're going to change it. We're going to use different conditions, so we're not going to use it anyhow. But in the next slide, I'll show what it implies, so you get a feeling of how strong that condition of Savage is. And he had another condition for non-simple act, but we will not, for simplicity today, only simple acts, only finitely many outcomes, so we need not mention that. Then Savage has his theorem. First, he has to start with his non-necessary axioms that are restrictive. That's the P6 mainly. Also, he needed a sigma algebra. I told you we need algebra. Savage needs a sigma algebra of events. With those restrictions accepted, we get if and only if, which is nice. Then his intuitive condition, I showed you, hold if and only if expected utility. So that was his preference foundation, his axiomatization. Well, something that implies, gives you a feeling, convex ranges is implied by that condition. That means if we have an event, non-null event, positive probability, then for any number smaller than that probability, we can find a sub-event that has exactly that probability. So you have a sort of continuum richness within every event. So no atoms and things like that. And a complete space, completeness, that's implied by the condition. That's a bit restrictive, maybe. We will generalize a bit. So now we go to our theorem, our conditions. Well, the first 5 are like Savage, although we only need algebra events, not a sigma algebra. Instead of his P6, we do different things. We take 2 axioms that replace his P6. The first is Archimedeanity, and that's necessary anyhow, so that doesn't impose any restrictions. So that's in itself, that's quite nice. Archimedeanity says, imagine you have a sequence of events. Imagine they're all equally likely. They are disjoint, and they are non-null. Then the condition says, this sequence must be finite. It cannot be infinite. It's quite easy to see that that is a necessary condition, because if it were infinite, then the probability would add to infinity, and it cannot be. Probabilities can never add to more than 1. So it's surely a necessary condition. It's not restrictive. That's one condition we impose. Then the second, this is our restrictive condition. This is what we have restrictive, unfortunately, but you always need it. Instead of Savage, we call that event-wise solvability. So I'll tell you what it is. Imagine we have a preference. We rather have the right act than the left act. And you remember the notation, the left act is specified here. Then on event B, you have an outcome beta. And maybe you may remember beta usually means a bad outcome. So imagine you want to improve the left act to get indifference. So you improve the outcome beta. You improve it into a good outcome gamma. Gamma is, you can see from this that gamma must be better than beta. But imagine the improvement is too much. If you do that, you get something that's better than the intermediate act. So you kind of, if you want to get indifference, you have been overshooting, improving too much. Well, the condition says if you are in that situation, you can always do the improvement on a smaller event. You shouldn't do it on all of the event B, but you only do it on a sub-event B1 of B, a smaller one. You can always find that sub-event exactly such that you get indifference, sort of solvability. So if we have this situation, we can define a sub-event B1. So then B1 and B2, they partition the event B. On the event B2, you don't improve, you keep beta. But on event B1, you improve beta into gamma. And then this should give indifference. So this condition means we have a richness in events like Savage. We have a sort of solvability. But it turns out to be weaker than what Savage had. We don't need a continuum for this, things like that. Anyway, this is our restrictive condition. And then, okay, this is in words what I already said. Like the intermediate value property of functions, but only in the event space we have it, the state space. So now we have our theorem. So our restrictive condition that we must first assume that is that P62, that is this event-wise solvability is what we need. And the rest is necessary and sufficient. We do only algebra, we don't need sigma algebra. So then we get all the axioms except the non-necessary one, if and only if expected utility. This is our theorem. So we generalize savage a little bit. The main point of our paper is a beautiful proof. We think we have a much easier, and we claim a beautiful proof. But we also have a bit generalization. For instance, we can have atoms, well, algebra of events, that's one thing. No sigma was needed. We can have atoms. We can have a finite state space. Savage can do. I should be a bit modest here. Only very particular, and not at all in general, only very particular examples of that kind. They don't bring much more generality, but they do show that we're really doing something different than Savage, so that we're more general than it shows. We can have a few cases of that, only limited, but a few. Then, also, if there are no atoms, still we have more generality, but okay. So that is structurally general. Structurally means in every situation where the Savage axioms holds, our axioms also hold. So it can be applied. But there are situations, like here, where our axioms hold but Savage don't. So that makes our theorem more widely applicable, more general in a structural sense. But it's also more general in the logical sense. And by that I mean, once you have, once you have our theorem, then you can get the Savage theorem as an easy corollary. So you don't have to do the proof independently. Once you have our theorem, it takes 1.5 pages. We'll do it in the appendix. You can show that Savage axiom imply ours. So once you have our theorem, our simple proof, one more page to read, and you have the Savage proof. So those of you who don't like, who prefer the Savage theorem to our theorem, like find it more prettier, then still you get a much easier proof here, because it's an easy corollary from what we do. So the main contribution already said, beautiful proof. We claim it, with figures. And the key idea is Hölder's lemma. You know, I told you a little bit about it. That's the tool we have. That's our secret weapon, so to say. But I should say, you need not know this. Our proof is self-contained, and you need not know anything about mathematics. You need to know topology, nothing. It's completely elementary construction. The only thing I tell is, if you think that we're doing very smart things in the proof, well, not so much, because we're just copying what Hölder did in his proof. That's what makes our life so easy. So in that sense, we use his ideas. But you need to know it. The whole proof is self-contained. You can just read it Saturday evening at home. You need nothing else than our paper to understand the most beautiful theorem in our field. So with that, now I tell you a bit about the proof. I can claim that in 2 or 3 hours reading, everybody who doesn't know about mathematics can completely understand every detail of the proof, but so much time I don't have. What I want to show in the time that I have is to convince you that you could understand the proof in 2 or 3 hours. So, so sometimes I'll show you figures, and then I don't explain what's going on, but I tell you, look, from the figure, you could understand it in 15 minutes, right? And then 30 seconds later, I go on. So sometimes like that, I skip steps. But then you also get the feeling of the gist of the proof. So that's how I'm going to try to do things. So then the proof. I start with a preparation, some properties of the preference relation, that they are nicely compatible with the set structure, the union of events. I'll explain what is going on later. And then I'll construct probability measure, construct utility function, and then I show that they work well in the EU formula that we want. That's more or less the proof. And I'm going to start with some preparatory things. That people who know the lemma of Hölder, in the lemma of Hölder you have a generalized addition operation, you have an ordering. Those two should be compatible. That's the main condition. This is only for specialists. But specialists can see that we're just doing that. We're taking this joint union as a generalized addition operation, and we show that our ordering is compatible with it. So that's why we're just copying lemma Hölder, why our life is so easy. So one example, if an event A is weakly, meaning in the betting sense, you rather bet on A than on B, that's how we defined it. Then if we add a disjoint C to both of them, it doesn't affect preference. This means in the Hölder terms, that event union is compatible with ordering. That's the first implication of the Savage axioms. And all our proofs are figures, very easy. So a notation, you know by now, good is better than bad. Now here I depict, you get always beta, only on the IA you get the good outcome. Here always you get the bad beta, only on B you get the good outcome. If you prefer getting on A than on B, that's what means A is revealed more likely than B. So here I depicted the definition of that thing. Here I depict the definition of that thing. You can choose, you get the good outcome gamma on A union C, or you get it on B union C. That preference means you rather have it here than here. So this is just depicting the definition of that thing. And then it's no more than a sure thing principle to say that they are equivalent, because a sure thing principle says your preference is independent of common outcome. And the only thing different between this and this is that the common outcome beta here is replaced by the common outcome gamma here. So the sure thing principle says these things are equivalent, and we have it proved. And then those who know Lemmershulder know, we are in business here. Yes, we are. Sure thing principle does it. Some implication of it, if we have two events A1, A2, and B1, B2, if A1 and A2 are bigger than B1, B2, then so is their disjoint union. This is another result to show that event unions are compatible with preference. And the proof, and now I'm going to do this thing I already told you, I'm going to show you a figure, and I will not explain what goes on. But just that you see it's easy. We have a way of depicting acts, and I will not explain how this works, why this is a picture. But there's an easy way to depict acts, and then the plus act is preferred to the minus act. That's the first assumption we do. For the second, we make the same figure. And then the sure thing principle says that common outcomes can be replaced by other. In the figures, it means we have a green common thing. We can take it out, and we can add a green common thing if we like. I'm not explaining to you what it is, but roughly how it goes. For this, we do the same. We take out that green common, we put in another green common. The sure thing principle says we can always do it. I just showed you. Transitivity, turns out that the worst one there is the best one here. Transitivity gives something here, and that turns out to be, we can add green parts as we like. And then we have what we should prove. And you couldn't understand what was really going on, but I hope you can understand that in 10 minutes you could completely understand this proof. And we don't have those 10 minutes. But maybe you should now compare this with the best proof in the literature of the Savage theorem is in a nice Fishburne 1970 book. Fishburne has a proof of this lemma of 2/3 pages. You take the left side of equation 2, the right side of equation 4, you substitute in equation 5, and then by transitivity you get equation 7.73 prime. That's the thing you have to read and see really hard. This is you're watching a movie. It's like that, it's just fun. You see it, just figures, and it's all pretty, and no effort is needed. And that's the idea of our proof, that you think you feel it, you're watching a nice movie. You like to see it, and then the proof is done, you're disappointed because you wanted more. We hope that you feel that when you read our proof. And it's quite different than other things you saw in the literature so far. Anyway, it means if two indifferent, if A1 and A2 are indifferent to B1 and B2, so is a union. You can repeat that if you have n indifferent, A1, AN, all indifferent to B1, Bn, then so are the unions. These are all kind of conditions. I'm a bit fast here. But the summary of all these things I'm showing you is that the preference relation and the event operation are compatible. They always behave nicely. That's one way to summarize what's going on here if you don't really understand, which you can't because I'm a bit too fast. But then with that understood, we'll be using it throughout construction of probability. First, we define the probability measure. And we use almost uniform partitions. I'll show you what it is. We start with a small event A1. And then we're going to take replica. If you read this beautiful Kranz et al. Book, The Foundation of the First Sect, they say quantitative measurement, you always start counting. So let's count. We start counting A1, we take a replica, A2 is equally likely as A1, A3, AN, we go on until we can't do more. So these are all equally likely. We go on until the rest event is smaller, so no more additional replica can be done. We have a partition, it's almost uniform. Uniform means they're all equally likely. It's almost uniform, but it is ugly duck here. That's a bit messy, but okay, almost uniform. Savage used these a lot, but later he could prove that he always had uniform partition. We don't have that. For us, really uniform partitions need not exist. We really have to work with this, but we can do it, it's no problem. If we have this, then we can say that the probability of the event A1, if we have this, and if expected that holds, well, we don't know, we have to prove, but if it holds, then we would already know that the probability of A1, we know quite precisely what it is. It must be smaller than 1 over n and bigger than 1 over n plus 1. So we have already quite precise boundary. So if we're going to define probability, gambling on expected utility to hold later to be proved, we're going to have upper and lower bounds like this. We also have upper and lower bound for all the unions of these events. You can derive it from that. So for a lot of events, we already know quite precisely how big the probability is, up to 1 or 2 over n, in fact, already. This gives us upper and lower bounds. If we have a general event, we take some general event, capital E. We can take any very refined, almost uniform partition, and then we can sandwich the event. We take the union of events, the biggest one that is smaller than A, and the next one that's bigger. And then we know the probability of event E must be between this K and K plus 1 over n plus 1. Well, we get boundaries. So for every uniform partition and every event, we can derive an upper bound and a lower bound for the probability of the event. We can just do that, but then we have to hope and pray that we don't run into inconsistencies. If one day it would happen that one almost uniform partition gave an upper bound, another one gave a lower bound, and the lower bound was bigger than the upper bound, then we have a contradiction, we can't do it. Then we would know that expected utility is violated. So we must surely verify, if we are happily doing this, that we will not run into contradictions. We must use the axioms to show that, but we can do it. Anyway, so we can do that. So we can prove that all these upper and lowers are consistent, and because they get closer and closer to each other, then exactly one probability number results as a limit. To show that consistency, that every upper bound is bigger than every lower bound that we get, and here is the figure that does it. And again, I'm not going to explain this figure, but the idea is if you have one upper bound from one partition, one lower bound from another, you take a much more refined partition, and that much more refined partition you can show, you can get some event that is between the upper and the lower bound of the other, so that keeps them apart so they don't bite each other. And we don't have the time, but in 10 or 15 minutes you can understand that figure, I think. Maybe that you can get from it. So then again, not much time, and just watching figure or watching a movie, just no mental effort is needed. I hope that you can take my word for that. Anyway, so then we have all these numbers, unique limits, probability numbers. We must prove additivity, and that's quite easy, but actually I'm a bit, given time, I want to skip a few things. Additive is easy because the lower bounds are additive, and then the probabilities are the limit of lower bounds. It's one of the more easier things. Let me go to construction of utility, because I'm going to do only the utility between a lower outcome and a higher outcome, small m and capital M. Only between those, I'm going to construct utility. The others you can extend, you can do it. So to keep it easy today, only we're going to do that. We normalize the lowest utility to 0, highest utility to 1. And then, actually I always like mathematical, I'm imagining I'm doing an experiment, measuring from subjects, that ensures that you always make constructive proofs. So if I define utility, I ask myself, how do we measure it in an experiment? All my papers, I try to think like that. It's usually done empirically using the standard gamma method, so we do it in the proof also. What you do, for an outcome alpha, you look at that outcome, you find here, you partition the universal event into an event as superscript alpha and the rest. Here you get the good outcome, here you get the bad outcome. You do it in such a way that you get indifference. Event solvability guarantees always can be done. And then, well, empirically this is called the standard gamma method. So this act is then the standard gamma for that outcome. And then expect you simply, if expected utility holds, utility of alpha must be that probability. Of course, we don't know if it holds, we have to prove it. But we're going to define this way, and then again, we're going to show that we don't run into contradictions. Now, using the empirical literature to learn how to write proofs. 1986, there were McCord and Neville, and they said, these measurements don't work so well because there's much trouble because of certainty effect. Better avoid certainty effect, better measure only conditionally. What you do, you take an act somewhere outside, you just fix things, getting rid of certainty. Only on a condition on some event A, you take the outcome, and here you replace it by a conditional standard gamble that gives you indifference by splitting up the event A, where you have the good and where you have the bad outcome. And you use this to measure utility. Well, then if expected utility were to hold, we should hope and pray that the utility that we got from the unconditional standard gamble is the same, because here the utility of alpha will be the probability of that event times 1 divided by the probability of that. That will follow. So we must hope that if we have such an observation and we write this, that we get the same utility number. We must prove with our axiom that that is really the case. And the answer is yes, that is the case. And I'm going to skip the proof, most of it. I'm only going to... Anyway, what we do, we take the constant alpha so that we could do the unconditional standard gamble. But then we're going to do the conditional standard gambles. And with a bit of reasoning I'm going to skip, from this you can see that the conditional standard gambles must be the same as the unconditional. And that would then imply that equality that I told you. And I want to skip. The only thing I want to tell you is, in fact, in this part of the proof, we are ensuring that the multiplication operation in expected utility is behaving properly. But we don't need any mixture for that. We only need addition. We're adding here conditional standard gamble. We only use this Hölder technique. Multiplying by 10, you can also do by adding 10 times. And that's enough to get everything you want. So if you study the proof carefully, here you see one reason why we can do without mixtures. But I didn't explain much. I rather, the time left, I want to use for the point where we have most improvement of Savage. Where we really, because Savage, poor guy maybe, because he wanted to go through phenomenon extent. So after he had all the probability, first he wanted to show that his structure is just as rich as a risk structure. He needed to ensure that he has all the probabilities for that. Then he needed to prove probabilistic sophistication, that the probability distributions capture all the relevant information. Then he had to derive the phenomenon axiom from his axioms, and then he could use the phenomenon. That's all roundabout. If you're here, you can immediately just write the expected utility formula. I'll show you now. So here we have a big improvement over Savage because we use this Hölder lemma thinking. You can get expected utility simply by adding conditional standard gambles. So now comes a huge improvement over Savage. So with all these things, of course, many things you couldn't explain, I was too fast. Here we have a general act giving x1 on the event E1, xn on the event En. And it's almost trivial. Though if you had understood what I said, you would say, of course it's trivial. You just substitute the conditional standard gambles and you add, and you're done. Nothing happening. So I do it. For every outcome, I substitute the conditional standard gamble. I did it for all the events, capital M, small m. Means I have only 2 outcomes. Means here we are getting the capital M under the union of the upper events. We get the bad small m under the complement of that. And this is equivalent. That's how these standard conditional standard gambles were defined. Now we're going to be very interested in the probability of that event. That we're going to like a lot. So what is that probability of that event? First of all, it is the sum of the separate probabilities. I already proved you this probability measure that we defined as additive. Hölder lemma is just that sum. Now I'm going to rewrite that. Let me put it up. Because I hope, well, I was a bit fast, but for every conditional standard gamble, this probability ratio is just the unconditional utility. I showed it a moment ago. But if that is true, that means I could just replace this by that. This ratio is just that utility. So this is the same as that. I just proved it a moment ago, but I was too fast for you to read on. But that was what happening there. So I can write it that way. But I assume that you start liking this formula a lot because, wait a minute, that is just the expected utility that we see standing there. That means this is just that probability of getting the good outcome is simply what the subjective expected utility formula calculates for that act. Now that is really nice because the higher probability of getting a good outcome, the more you like it. That means the higher the subjective expected utility, the more you like it. So that means I have now proved that subjective expected utility represents preferences. I've proved it. And now I must warn you for disappointment coming, because this is the end of the proof. Nothing more to be done. We're already done now. So nothing more than your few figures on a Saturday evening, you're relaxing, you're watching the movie. And now, it's already the end of the movie. That's how I hope you will read our paper. And then maybe you should also read the proof in Fishburne 1970 to see the difference. Sorry?
The proof of the lemma that you were mentioning, I was never sure whether it was right or wrong. I mean, the proof is undecidable.
You mean a Fishburne? I hope you do refer to Fishburne, not to us, right?
I tried it a number of times, and I tried to evaluate it, but it's undecidable. Copy of proof works, and
The
that's
copy,
the
yeah.
state of the art.
Yeah, it's indeed. I told you in the beginning of this lecture that few people wanted to touch Savage. Everybody's answering, but maybe 10 or 15 people have done it. And Kopilov did very advanced general thing. He's the most impressive guy on the Savage structure. Yeah, but like everybody, he did like Savage. He goes to the risk structure. He does that roundabout thing. So we should send him this paper. We'll save him a lot of time from now on. Yeah. Actually, there's a part in the proof of Fishburne where he goes from local to global optimization. And I think he doesn't really prove that one, he just claims it. There is a part in his proof that I did not, maybe it's the same as you. Yeah. So there are some things still, but here there's no mystery at all. Just anyway, so then conclusion. So this Hilde technique is very powerful. And like this proof, when I'm proving a mathematical theory, I'm imagining I'm doing an experiment. And also here, always I was how do I measure in an experiment? And then that's how I define in the proof. And in the axiom, you don't want to have contradiction, you want to have consistency of measurements. Those are the axioms. So that, if you have that spirit, that guarantees you have constructive proofs. Well, I come from the country of the mathematician Brouwer, so then that means a lot, but there are many good sides to it. But I think it's compulsory for every speaker to leave 5 minutes, because otherwise the conference gets boring and speakers use all that time. So I should stop talking now.
We have time for a few questions. Philippe?
As a matter of history, Davidson and Soukis in the 50s had a result which perhaps you'd like to compare with yours. It seems much less sophisticated, but they did use a solvability condition, and presumably Hilde's theorem is in the background.
They assume that they have all equally likely events.
Yeah.
And then it's actually I only showed you the proof for the atom case, the atomless case, because that's the atomless case. We also have that's easy. In the atomless case, in our case, you can see that they actually imply that the universal event is a union of a number of equally likely atoms, and that is like this Substance and Sequel. Substance and Sequel both have to prove also the experiments. That's what I always like. For our field, it's good if you have both together. Davidson, Substance and Sequel. Yeah.
And more technically, how do you go from simple acts to general acts? I mean, presumably you need to reinforce the sure thing principle.
It's indeed, we don't do that in our paper. We want to do simple because there we have a contribution. Going to the non-simple is like Savage, you need P7. P7 is beautiful for doing it. The other ways, yeah.
Isn't it enough to reinforce the sure thing principle?
Well, actually,
and the solvability?
In fact, P7 can be considered to be a sort of reinforcement of, it's much the spirit. Yeah. So yeah, that's a way of putting it, yes.
Next question.
So you said you could have simple state space?
Finite, yeah.
Finite state space.
Yes.
And understand how you can have that with solvability.
Well, if you have, in the finite case, always the state space is a union of equally likely atoms. And because they're equally likely, you can get the solvability satisfied, even though it's finite. You also need a finite outcome space then. So it's quite limited. We don't have much, but we have a bit. But you can have it done. We give examples in the paper.
There's a paper that's called Studied for Finite State Space. I think it's from Shu or...
Cool.
So you have maybe a way of saying how you generalize or...
Well, Gould, there have been other people before Gould who already did Savage for finite state spaces, but these guys, they all, Brigitte Groder was the first, I think, with Calvin, but she on her own. Anyway, these papers, they use a continuum of outcomes. So this is continuum of states. If you have continuum of outcomes, you get different theorems, and that's also nice. That's Enskamp-Aumann, Savage richness of space, states, and richness of outcomes is a third way to do it. Also interesting.
When you did a step in the proof, I think it was the first lemma, you said that you can do it just with the sure thing principle. But in fact, I think think that you implicitly use the P3 as well. Because when you add this extra event C,
Yeah.
you implicitly assume that the alpha beta on C are the same,
Yeah.
you get the same ranking. So implicitly
Yeah.
there is state independence there, or they're not state
Ah, that's indeed what gives state in the. Oh, I should have known RDSE. I should watch my words. You are right.
More questions? Okay, thank you.
Thank you.